Hey guys, hope everybody's doing okay. What we're going to do today is continue with Hess's Law. This is the second part of our Hess's Law lecture, and we're still going to be finding the enthalpy of reaction for chemical reactions, but we're going to look at it in terms of two different approaches here. The first approach is similar to what we did in part 1 of our Hess's Law lesson, and the second approach is still related to the first one, but is a little bit of a shortcut that I'll show you guys how to use. All right. The shortcut makes a lot more sense once we go through the longer process, which we still need to be familiar with. So the longer process that we're going to start out with today has to do with a standard formation equation. Now, we looked at these earlier on in the year when we did our Born-Haber process, or the Born-Haber cycle, when we looked at the formation of ionic compounds. So if you might remember, we had to break all of our bonds, lose electrons, gain electrons. We had lattice energy, right? We had to write formation equations to do those types of problems. So we're going to do the same thing here in our thermodynamics unit, our Hess's Law problems for today. So let's review how to do that. Standard formation equations are when you create 1 mole of substance from elements in their standard state at standard conditions. I'll define standard conditions on the next slide. I have 3 formation equations on the screen for you. The first one is a formation equation for hydrogen peroxide. So again, we're creating 1 mole of that. And the elements in their standard state at standard conditions are hydrogen and oxygen. So they're diatomic. So H2 plus O2 yields H2O2. Pretty easy. The next one is the formation equation for water. Now again, we're creating 1 mole of water here. So we have H2 plus 1/2 O2 yields H2O. So remember, these still should be balanced, right? So we have 1 oxygen atom here. We need to make sure we have 1 oxygen atom here. And in order to do that, we have to put a coefficient of 1/2 in front of the O2. I know that looks weird, but remember, the formation equation is 1 mole of compound. So we have to make sure our product coefficient is a 1. Finally, we have formation equation of table salt. So we have Na solid plus 1/2 Cl2 produces NaCl. So let's see if we remember exactly how to do this, and we'll do 1 or 2 practice problems. Let me define standard conditions first. Standard conditions are different than, they're different from STP conditions for gas law problems that we may do. So standard conditions we're going to use in our thermodynamics unit, which is what we're in right now. We're also going to use standard conditions a little bit later in our electrochemistry unit as well. All right. There's only one main difference here, and that's the temperature. STP for gases and gas laws, standard temperature was 0 Celsius. Right now, standard conditions, not STP conditions, but standard conditions for thermodynamics and electrochem, we have a temperature of 25 Celsius. Okay. Pressure, 1 atmosphere, that's similar to STP. And standard state just means what state of matter is the substance normally found as. So most things are solids, but we do have a couple liquids. Remember, our 2 liquids at room temperature are bromine, which is also diatomic, and mercury. And remember your diatomics, your 7 diatomic elements on the periodic table: NOF, Cl, Br, I, and H. Okay? So just keep those in mind as we progress through and write our formation equations. A little bit of confusion when we get to this part here with the delta H. Students are like, well, I saw a delta, or actually a delta HF. Students are like, well, I've seen this before, and you're correct. So we do have a delta HF. That's the heat of fusion from earlier on in this unit. That's the energy required to transition from a solid to a liquid, right? The melting process. That's the phase change that occurred there. You also have a delta HF with the enthalpy of formation. So yeah, the same notation is used for both, but the problems are so different that you're not really going to have to worry about confusing the two. If you have a phase change and you're looking at the energy required for that to occur, to go from a solid to a liquid, of course it's the heat of fusion. And we've even talked about that in earlier units as well. The enthalpy of formation is when we're doing something like this with some Hess's Law problems. I want to see the energy required or released when some compound is created, right? You do see this little degree sign. That just means at standard conditions, which I just defined for you. So if you see delta HF with a degree sign, it's the heat of fusion, obviously, if you're talking about the earlier part of the unit, and the enthalpy of formation, which is what we're going to focus on today. All right, so don't worry about confusing the two. The problems are so different involving these that you shouldn't really have to worry about it. So to do a quick review of formation equations, let's look at zinc oxide. We're going to have to write this one a little bit later anyway for the practice problem we're going to do. So we have zinc, and that's a solid in standard under standard conditions. Oxygen, diatomic gas under standard conditions, and it produces 1 mole of zinc oxide solid. So that's why I have the 1/2 in front of the O2, because the zinc oxide only has 1 mole of oxygen in it. I need to make sure the equation is balanced. So that takes care of our formation equation of zinc oxide and our quick review on all that. Something else I want to talk about before we get into the problems is, first of all, where you find these standard enthalpy of formation values. They are usually provided for you on some sort of reference sheet. If you look in your packet, if you flip ahead a couple pages, or if you go to the very end of your packet, you have some reference pages with a lot of these values on it. So you have the delta H values. We'll eventually look at delta S, which is entropy, and Gibbs free energy, which is delta G. So some of the pages at the end of your packet have all those values. But I want to point out here a little bit of a pattern. Let's look at H2 in the gas state. The standard enthalpy of formation is actually 0 kilojoules. Same thing with strontium solid. There's a couple other ones on here. Carbon solid, oxygen gas solid. All of those are 0 because look at what you notice about these. All of these are the element in their standard state under standard conditions. So hydrogen's formation, the enthalpy of formation, the energy required to create H2 gas is 0 because it's created. It's there already. Okay? Look at the one above it where you have hydrogen gas, and this is just the monatomic hydrogen. That's not how it's naturally found. Since it's not naturally found that way, there's going to be some enthalpy of formation required to make that, okay, to make that monatomic hydrogen. So notice all of them with 0 here are for the elements in their standard state under, in standard conditions. If you look at the strontium ion, it's not like that's not its elemental form. That's not its standard state under standard conditions. The standard state under standard conditions is strontium solid. If you look on the periodic table, it's clearly a solid metal, right? So the Sr+2 ion has to have a formation, an enthalpy of formation value there, all right? So it's key to remember that elements that are in their standard state at standard conditions have an enthalpy of formation of 0. We're going to look at how that applies in just a minute here on our practice problems. So the enthalpy of a non-formation equation. So the formation equations, especially for like this one here, formation equation for zinc oxide, you can just look up that delta H value in a reference table somewhere. But what if you have an equation that isn't a formation equation? So you have some non-formation equation, non-formation reaction. How do you find the heat of reaction or the enthalpy of reaction for that? Well, what you can do is use all of your formation equations for the various components and just go through and do a Hess's law style problem from the previous lesson. Let's look at an example. Doing an example is a lot easier than me talking about it. So I want to find the enthalpy of formation under standard conditions for this chemical reaction. All right, so let's figure out what it is. We're going to start out by doing our formation equation for everything. All right, so let's go ahead and do that. Formation equation for zinc sulfide is what we're going to do first. So that is simply zinc plus sulfur. I'm not putting the states here, so I could write it a little bit faster and so I don't clutter up the screen. Okay, zinc solid. I'll verbalize it though, so you know what they should be. So you should write it in, but I'm just going to try to go a little bit quicker here. Zinc solid plus sulfur solid produces zinc sulfide, solid. And if you look in your packet, the heat of formation under standard conditions for that is negative 202.9. And that's kilojoules per mole. Okay. The next one, the formation equation for O2, here we go, just like a slide or two ago. Oxygen gas, that is the standard state under standard conditions. So O2 gas will have a heat of formation of 0 because it's already made, right? So you're not going to have to worry about that. So we're going to actually just cross off. Let's look at the next one. We have zinc oxide. We just did that. So we have Zn solid plus 1/2 O2 gas. I put the state there for some reason. Produces 1 mole of zinc oxide solid. And the heat of formation for that, if you look it up in your table, is negative 348.0 kilojoules per mole. Finally, we have sulfur dioxide. So we have sulfur plus oxygen gas produces sulfur dioxide. Look at your reference table, and you can find the delta H value for SO2 as negative 296.1 kilojoules per mole. What you want to do now, it's really easy. You want to look at all of these formation equations and manipulate them so when you add them all up, you get the overall equation at the top of the screen. Okay? Simple stuff here. Zinc sulfide has to be a reactant in our overall chemical equation. If you notice, for your formation equation, zinc sulfide is a product. So what do I need to do to this first chemical reaction? I definitely need to flip it, right? I need to get the zinc sulfide on the reactant side. I also need 2 moles of zinc sulfide instead of 1. So I need to not only flip this reaction, but I need to multiply it by 2 as well. So multiply by negative 2. The oxygen we're not worried about. It gives us a 0 kilojoules per mole anyway. So we'll have to get our oxygen from the other components. Zinc oxide is a product, and in your formation equation, it's a product here. The only difference is I need 2 moles of it, so I'm going to multiply this formation equation by 2. Finally, SO2 is a product. It's a product here, so it's already on the right side. But again, I need 2 moles of it. My formation equation only gives me 1, so I'm going to multiply this formation equation by 2. I'm going to clean this up a little bit. I'm going to rewrite these underneath. You guys can do the same thing. Let's then find our heat of formation for this reaction and see what cancels out. So first equation, I'm flipping it and multiplying by 2. So I get 2 ZNS yields 2 ZN plus 2S. My delta H of formation value of negative 202.9 has to be multiplied by negative 2. If you do that, you get a positive 405.8 kilojoules per mole. Again, oxygen, not worried about it. Next one, I'm just multiplying by 2. So I have 2ZN plus O2 yields 2ZNO. I take my formation of that of negative 348, multiply it by 2, and I get negative 696 kilojoules per mole. Finally, last one, multiply by 2, 2 sulfur plus 2 O2 yields 2 SO2. I take my negative 296.1, multiply it by 2, I get negative 592.2 kilojoules per mole. Cancel out what I can. 2 zincs on that product side, 2 on the reactant side, 2 sulfur on the product, 2 sulfur on the reactant. Looks like that's about it. let's combine everything, make sure it works out. 2ZnS plus, right here, you have 3 oxygens, produces 2 zinc oxides and 2 sulfur dioxides. Take all of your delta H values, add them up. 405.8 plus negative 696 plus negative 592.2. You get a grand total, positive, actually, not positive, obviously. We have a negative 882.4. Okay? Okay, guys, so it's quite the process here to go through and get that. It's not really difficult, I'd say, but it's definitely a little bit of work involved. So again, you are going to write your formation equations for everything in your chemical reaction. Don't worry about like zinc sulfide. Don't worry about it being a reactant until later. Like remember, follow your general rules here. Your formation equation is where your compound is a product, 1 mole of product from the elements in their standard state under standard conditions, and those are going to be your reactants. Okay. Once we write all of our formation equations, then we can worry about manipulating those to get our reactants and products on the correct side based on our overall chemical equation. All right. Let's go ahead and try one more. Okay, so you guys can go ahead and try this one. So if you go to a page later on in your packet, you'll find this problem where you have NaOH solid plus HCl gas produces NaCl solid and H2O gas. So do the same thing. Write the formation equation for all of these and then manipulate it. Use the information in your packet on that page. I think it's in the bottom right hand corner. Or maybe it's the page before it. It's near there in the bottom right hand corner, and find out what your heat of formation is for that process. Okay. Just to help you get started a little bit, don't be concerned about sodium hydroxide having 3 elements in it. Just follow your general rules for a formation equation. You're going to have sodium solid plus 1/2 O2 plus 1/2 H2 to give you 1 mole of NaOH. Okay, so we have to make sure it balances. You need 1 mole of O, 1 mole of H on the product side. So you got to multiply your O2 and the H2 by 1/2 on the reactant side because they're diatomic, right? So that's what your formation equation looks like for that one. Do it for HCl, NaCl, H2O, put them underneath, and then manipulate, do what you got to do. All your coefficients here are 1s, so it shouldn't be too bad. Let's see what we get. Alright guys, so the solution here is on the screen. You can see that the formation equation I started you with is right here. The other formation equations are underneath it, all pretty standard. We've actually done a couple of these already. And then the standard formation enthalpies are here. You can see I manipulated underneath, so I had to flip the first reaction, and I also had to flip the second reaction. The third and fourth stayed as is. You can see what cancels out, all works out very nicely. So you multiply the first and second reactions by -1, and you end up with a total enthalpy of reaction of -133.7 kilojoules for this practice problem. Okay, so if you didn't get that, you can take a look at the screen here, see where you made your mistake, and we'll move on from here and talk about a shortcut for how to do this. Okay guys, so to wrap this up here and looking at the shortcut for how to do this, you want to write down that equation that you guys have on the screen here. Write that on your note sheet somewhere. And that is that delta H is equal to the sum, so that symbol is here, this is the sum of the number of moles times the enthalpy of formation of your products minus the sum of the number of moles times the enthalpy of formation of your reactants. This is basically what you just did on the last, in the last couple practice problems. If you go back and think about it, if you go to the one that we did first as our class example, you wrote the formation equation for zinc sulfide, right? And that was zinc plus sulfur produces ZNS. And you know you had to flip that. So whatever your delta H value was, you had to take the opposite of it. Okay? So I forget what it was, but say it was X kilojoules per mole. You had to take the opposite of it and do minus X, so, or subtract it, right? So if you look at what we end up doing here for our shortcut, if you look at your chemical reaction, like if we did actually write the formation equation for all of these things, what you would have to do is, when you write the formation equation for carbon monoxide, that's carbon plus 1/2 O2 produces CO. It's going to have some enthalpy of formation, right? What you're going to have to do is flip it. You're going to have to take the opposite of that because we want carbon monoxide to be a reactant. So you're always going to end up flipping the formation equations of your reactants in your overall chemical equation so we can get them, or from the formation equation, we can get them on the correct side. So this shortcut, this equation here, is kind of telling us that we're doing that, right? So it allows us to skip that whole process of actually writing the formation equations because we know what we have to do anyway. We know we have to flip all the formation equations of our reactants and keep all the formation equations of our products and those values as is. The only thing we would have to do to completely fix it is make sure we multiply by the correct coefficient. And that's why we have the N value here. Or not the N value, but N stands for number of moles. That's why we have that as part of our shortcut equation that takes into account the coefficients in your balanced chemical equation. So let's go through and do this example. Let's see how extremely easy this is, really short, way less tedious compared to what we have been doing. So my delta H for this problem is equal to the sum, that's the best I could do, the sum of the number of moles, which is 2, times the enthalpy of formation of my products, which is, I only have one product here. So it's the sum of 2 times the enthalpy of formation, okay, of CO2. That's the only product I have, minus the sum of the number of moles, which is 2, times the enthalpy of formation of carbon monoxide, plus, I have another reactant, 1, there's a coefficient 1 in front of oxygen, heat of formation of O2. All right, let's go through and actually put in our numbers here. So you could look these up at the end of your packet. So there's a big table at the end of your packet with delta H values there. It also has some delta S values, which is entropy, and delta G values, which is Gibbs free energy, but that's a story for another day. So you could look at the last page or two of your packet, that reference sheet. You could find all of your delta H values, your enthalpy of formation values at standard conditions for all these things. That's where I'm getting these numbers from, if you're wondering where all these numbers are appearing from. Okay, so we have 2 times the heat of formation of CO2, which if you look it up, it is negative 393.5. Okay, negative 393.5. It's kilojoules per mole, minus 2 times the heat of formation of carbon monoxide. And if I look that up, that is going to be negative 111 kilojoules per mole. I'm looking at my note sheet, making sure I'm telling you the right numbers here. Plus 1 times the heat of formation of O2. Well, guess what? That is 0 kilojoules per mole, because it's already in its standard state under standard conditions. So, simplify all this. 2 times negative 393.5 gives us negative 787. The mole, like this coefficient 2 here is 2 moles, and you're canceling that out with the moles in the denominator here. So we just get negative 787 kilojoules minus 2 times negative 111 is negative 222 kilojoules, right? The moles cancel, plus 0. I don't need to show that. So negative 787 minus negative 222 gives us an overall value of negative 565 kilojoules. Okay? You can consider this reaction, we'll get into this later, you consider this reaction as 1 mole of reaction. So sometimes you'll see an answer as negative 565 kilojoules per mole. And you're like, what the heck? I thought all the moles canceled out. It's negative 565 kilojoules per 1 mole of reaction. Just a term the College Board likes that we'll talk about more later. Okay? So there you go. That's how you do it. Simple. Take a look at this one. For the last example, I'll do with you, then you'll try 1 or 2 on your own. You have silver nitrate producing silver nitrite plus 1/2 O2. So it gives you the overall delta H for the reaction as 78.67 kilojoules. It gives you the heat of formation of silver nitrate, and it gives you, oh, that's it. You have to find out what the heat of formation of silver nitrite is going to be. So we go through the same process here using our shortcut. So we have delta H overall, right, equals the sum of your products. So we have 1 mole times the heat of formation of silver nitrite plus 1/2 heat of formation of O2 minus the sum of our reactants, which is 1 times number of mole, well, number 1 is the moles of silver nitrate. It's the heat of formation of AgNO3. Okay, it actually gives us the overall. So the overall delta H is positive 78.67 kilojoules is equal to the sum of 1 times the heat of formation of silver nitrite, which we don't know. Okay, so we have basically 1x plus the heat of formation of oxygen is 0. Remember? So 0 times 1/2 is 0 minus the heat of formation of silver nitrate, which is given to you, times 1. So, of course, negative 123.02 kilojoules per mole times 1 is just negative 123.02 kilojoules. Once you guys simplify that, you should get an answer of negative 44.35 kilojoules. And again, that's going to be your enthalpy of formation of AgNO2, which is silver nitrite. Alright guys, that takes care of it for today for the most part. There might be 1 or 2 more practice problems in your packet that are related to examples 1 and 2 here, so you can give those a try. Use examples 1 and 2 to help you solve those. And we'll talk about them when we get back in class and see how we did. Alright, thanks guys.